So, lesson 19, history of electricity. We will be able to describe the basics of electricity and charge. So we're going to go through the basic ideas of electricity. As I said, foundation, we're going to build our understanding of this. Plus, it's a really good point to, I guess, talk about, when we talk about electricity, I like to talk about our first ideas of electricity. Ultimately, compared to motion, electricity was only really properly figured out a little bit later after motion, but still it was a lot of the principles came very quickly. So we're going to start off with history of electricity. Our earliest idea of electricity comes from this. Can you guys give me a guess? What do you think is happening here? What do you think? What are these two objects that are being held, and what do you think they're doing? Who wants to take a guess? It's amber and fur. Good guess. Well, you're correct. They are. It is amber and fur. Now, what they would do is that they know, like early humans noticed that if you had a piece of amber and you rub that piece of amber onto a piece of fur or wool or whatever, that piece of amber would then have this ability. What that piece of amber could do is that piece of amber could then pick up small leaves and twigs and sticks. What people would notice is that if you had a bunch of leaves or sticks and stuff, is that the amber, things would actually fly up to the amber. And they would be attracted to it. And I guess initially we refer to this as, they would refer to this as like, I guess, some sort of magic, right? Because, you know, it's giving it properties. And this is actually where, by the way, amber is the English referred term for what this was called. The Latin or Old English of the older term, I think it was the Greek term for amber, was not amber. It was actually called electric, which is where the word electric comes from, electricity comes from, this idea of amber. This is our first idea of electricity. We later now know that the reason, what's actually going on here is that electrons have a stronger affinity to the wool than to the amber. I may have got this, I always get this wrong, so please don't quote this, but in general the idea is the electrons move onto the wool. And that means that if electrons move onto the wool, that the wool becomes negatively charged and the amber becomes positively charged. And the reason the amber becomes positively charged is because it's lost its negative charge. If you've got 3 negatives and 3 positives, if you get rid of some of the negatives, you have an overall more positive charge than negative charge. So that's why we say it's positively charged. Now, this is another thing that I learned recently from teaching physics, is that you can't tell. I used to always get confused. I'm like, okay, so if I rub a balloon, does the balloon become positively charged? What if I rub a piece of plastic? You actually can't tell unless where the electrons are going to go, unless you have a chart so you know it. So that's why this is a little bit of a guess to assume that the amber is positively charged. The idea is it picks up something called a charge. Now we're going to talk about what a charge is, but yeah, we'll get to that in a second. One of these things is they picks up a charge, and that charge they figured out could attract leaves and small twigs and stuff. But overall, over a certain amount of time, the charge would go away. And so then it wouldn't be, and once that charge goes away, it wouldn't be able to pick up the leaves and stuff like that. It would just be a normal piece of amber again. So there's only so much charge you could build up onto a piece of amber. But what people started to do is they started to experiment with new ways What if there was a way that you could store the charge? If you could store the charge, like, what if you could like take all the charge and put it into a jar and then fill that jar with charge, and you would have like a jar with just like lots and lots of charge in it, and you could use that later on. Well, the first way that they found they actually made this, a Leyden jar or a Leyden jar. Now, most people jump when they talk about electricity, they jump from talking about, oh, we have these old, you rub amber and that's how you get charged. And then they go from charge straight to the battery. And that's sort of what Everest was suggesting. And yeah, you know what? You are not wrong there, but the Leyden jar is actually something that I feel like a lot of teachers forget. And it's actually a relatively important thing. The Leyden jar was discovered independently by several different scientists around 1746. So a lot of scientists were coming up with this theory. The Leyden jar is a high voltage device with electrical energy collected within it from friction, maybe as high as 35,000 volts. The ball at the tip of the rod is a corona ball to prevent leakage of the energy into the air. So how does it work? So I actually built one of these, and this is one of the annoying things. I would actually show you guys what this looks like, because I actually built one. It's actually not that hard to build. You guys could actually even build one of these yourself if you're interested in shocking people, and it pretty much turns into your own personal taser. Of course, you've got to carry around a jar, but what you do is you start off with how do you build your own Leyden jar? What you do is you start off with a glass bottle. Or a plastic bottle. You know what? It actually doesn't matter. The example that I think I use a plastic bottle. It's good to use. My suggestion, by the way, for bottle type would be Fiji water, because it's a nice square bottle. But we're just going to draw a random bottle here. Now this bottle is made of glass. Now glass doesn't really conduct electrons well. Okay. What you do is you fill that bottle with brine. Now brine is aka salt water. And then what you do is you put a metal rod in the middle. What did I use for metal rod? I used a nail. So if you grab a nail, I learned this completely, by the way, from the King of Random. The King of Random built like a Leyden jar. They were able to get enough electricity built up over 6 of them to get a visible spark. But I just built one Leyden jar just to see how it works. And then what you do is you surround the outside with metal. And you guys are probably thinking, there's no way that I'm going to be able to get access to metal to be able to surround the outside of a ball, outside of a bottle. The answer is yes, you can. It's called aluminium foil. You guys probably have aluminium foil in your drawer at home, in your kitchen now. So with a nail, some aluminium foil, an empty water bottle, and some salt water, we've actually created ourselves a Leyden jar. Now what happens? How does this work? So if you have, let's just say you've got something which has got a, let's say you've got something which has got a lot of negative charge. Just say, what you do is you get, so let's say you got something that's got a large negative charge. It's got a lot of electrons to it. What these electrons can do is these electrons can jump onto this ball, and then they travel down and they stick around in the water. Now these negative charges will then lead to a buildup of positive charge in the metal around it, and you end up with this charge imbalance. And the reason that they don't cancel each other out is because the charges can't make it through the glass. The glass prevents, the glass doesn't conduct electricity, or plastic as well doesn't conduct electricity very well. So because they don't conduct electricity very well, it stays in there. And what you can do is you can then get rid of that rod. That rod will lose those electrons, and then you've got this charge. And the charge stays there because you've got this ball which doesn't conduct a lot of charge, and there's no conduction through the glass, the charge sort of stays there. So you can actually get another rod which has got more negative charge on it and further build up the charge. You can add more of them on there. And then that will lead to an even greater charge. And what people would do is they would then take a wire, and they would come away from this metal. In this case, it's an aluminium foil. And that wire is going to be positively charged, and the metal ball here is going to be negatively charged. And what they would see is that after enough time, you would be able to see a spark. And so therefore, that gave them this sort of way that they could test electricity. People could start to see sparks. You could generate the charge in a number of ways. I usually generated it by just getting a plastic rod and rubbing it onto some fur or actually it wasn't even fur. I would just use paper towel. That does a pretty good job too. And then passing it onto the setup. And over time, you build up more of a charge, and eventually, when you pass that charge you can create a spark. Now you can build up 35,000 worth of volts, so people are actually getting pretty significant charges. Of course, once that charge has happened, discharge has happened, that's it. You're done. That Leyden jar is spent. You've got to recharge it up again. But what it gave scientists an idea of, you also looked at the fact that you could also, with this setup, use it to attract small leaves. They started to get this idea that perhaps this charge that they built up on the amber and the charge that they could build up with the Leyden jar were linked. And also, if you can see electricity, potentially by a spark, perhaps lightning, the sparks that come down from the sky, maybe that's also a type of this same idea. Maybe the same way when you rub an amber against fur, that's almost the same as when the clouds rub together and they make electricity. So people are like starting to link these ideas together. But one of the problems with this is that you don't get a continuous supply of electricity. Once that electricity is done, you've got to build it back up again. So what they then discovered next was this idea of a voltage pile. Now, ladies and gents, if you're looking at this and you're like, wow, all these hyperlinks. Yes, I just copied and pasted this straight from Wikipedia. I got a bit lazy when I made this slide. I've had this slide for a couple of years. I've never updated it because it's just like, I usually just talk over it anyway, and I don't expect you guys to write this down. It's just me talking about it. So in 1780, Luigi Galvani was actually dissecting a frog, and what he had fixed this frog down with some brass hooks. And what he had was an iron scalpel, probably because he didn't have a steel scalpel, iron scalpel, same sort of thing. And he touched one of the legs, and he noticed that the leg of the frog twitched. Now, one of the things I always say to people is, I'm like, okay, if I was Luigi Galvani, and he goes, oh, this is interesting. If I was Luigi Galvani, I'd be freaking the F out. I would be losing my literal shit because I had probably at this point cut the head off the frog and half of its insides out, and then its legs started to twitch. I'd be like, holy crap, it's a zombie frog. But no, Luigi Galvani doesn't freak out and, goes to get like some kind of religious person to, get rid of the possessed frog. He goes, wow, this is interesting. It's like movement. It's like that movement of the paper or the small leaves, except it's happening inside of an animal. I'm going to call this animal electricity. And he actually used this to make a generalized theory of maybe this is what the soul is. The soul is like animal electricity. And this animal still has a bit of soul left because that's why it was moving. But essentially, this was sort of discredited later on by Alexander Volta. Alexander Volta comes along and he starts to look into it. He finds it interesting, the metals that were joined. When the metals touched, that may have been what happened. So he sort of makes this theory. He says, well, maybe we could actually force metal to do this. So he creates something called a voltage pile, which is, for those of you that are playing at home, the first battery. Now this, it actually looks like a battery. If you sort of squint a bit, you say, well, look, it's got a cylindrical core. It's got one end here, which is a bit pushed up, and another end, which is just flat. Yeah, this looks like a battery. And this is the first battery. And how we made it was you used copper and zinc plates. And these zinc plates were separated by some brine or some, which is again like this salty liquid, and that would separate the plates. And what you notice is that if you compared the top to the bottom, you could get a shock, you could get a charge of electricity. Now, why is this better than the good old Leyden jar? Because this is on demand. What that means is this doesn't run out. So you could run experiments on this voltage, on this electricity all day long, and you could get a large amount of do a lot of experiments. And it's still the same idea of electrons moving. They didn't know it was electrons moving at the time, but they started to really be able to do a lot more experiments. There is something different about this type of setup as well. It's not, this is like, I guess, electricity rather than static electricity, which is what we're going to talk about. Static electricity is built up charge. And the release is like that, and then it's over. Whereas this is, I guess, current or regular electricity. It keeps getting formed and it keeps going, even after you zap something or whatever. And it'll eventually run out, but it is able to make electricity. So this is what we have in the form of a battery. And so this is now, we're looking at 1800s when this is first coming about. So this is an interesting idea. This gets followed on to, I'm going to follow along with this to our first idea of electricity. This is probably one of the only slides that I'm going to get you to write down. So I'm going to put this up here. Electricity. Electricity is the process in which charge, this is what we understand now, is the process in which charged particles, which are electrons, in this case, are moved from one location to another location. That's our basic theory of electricity. Now you might say to yourself, charged particles, why didn't I just say electrons? Technically, if you could get like a lot of protons moving in a straight line, that would also be electricity. But the reason protons don't move is they're stuck because they're the nucleus. They can't really move around wherever they want. They have to stay where they are. Otherwise, yeah, you wouldn't have atoms. And you can have other subatomic particles that have got charge, but in this case, electrons are what we're talking about. They can move quite easily. So that's what we call it when we say, that's what we call electricity, is like the movement of charge, in this case, electrons. And yeah, so we didn't really have an understanding of what electrons were yet. A lot of you guys have done a fair bit of science, and you probably know that, you know, we discovered electrons and protons and stuff by Rutherford looking at the nucleus and atom and the plum pudding model. So that was all happening around this time. We still didn't have an idea of what electrons were. We certainly didn't know that they were strongly related to electricity, but still, we now understand this is what electricity is. I'm going to give you guys another 30 seconds to copy this down, and then I'm going to quickly go to the very last thing I want to talk to you guys about today, which is going to be a little bit about why electricity does the things it does. So so here's one of the questions that I usually ask before I even start any of the questions. Well, if electricity is when electrons move, why do electrons move? And that might seem like a weird question for you guys, But ultimately, that's the basics here. One of the questions that I asked with Newton's third law, if you guys remember, is I asked the question, well, how can anything move? If every force has an equal and opposite reaction force, how can anything move at all? So this question, why do electrons move, is actually relatively important. If electricity is movement of electrons, why do electrons move in the first place? Like, aren't electrons attracted to the positive nucleus? The answer is yes, but so why do they move? And I think this is a really good question that I like to ask. There are a couple of reasons why electrons move. The first reason that I usually give for, actually let me change the color. The first reason is, the main reason the electrons move is to fix an imbalance of charge. What that means, and that's the basic reason why electrons move. If I create an area, now if I create an area which has got a large amount of negative charge, and then I create another area which has got a large amount of positive charge overall, that means that this area has few electrons, whereas this area here has lots of electrons. So why do electrons move? The electrons move because they want to fix an imbalance of charge. You could also think about this is because the other reason why, but this is the same idea, and that's because electrons repel electrons and are attracted to positive charge. So if you go have a look, there's lots of electrons on the left and a very few electrons on the right. What's going to happen is these electrons are going to jump over there. And as these electrons jump over there, there is going to be more, that's going to be more electrons, and this is going to be, which is going to balance it out. This is going to end up with less electrons. And then overall, there's going to be balanced out. So the reason why electrons move in the first place is to fix an imbalance of charge. That's the main reason why, and this spark here, this is a spark. You might refer to this as light. Now that's fine and that's okay. It's an okay explanation, but in my opinion, this always begs the next question. This introduces the next question that I like to ask, which is this. If this is the case, which I'm like, okay, then how can an imbalance of charge be created? If electricity happens straight after to balance out a charge. If you've got an imbalance of charge, the electricity wants to jump in there. How can you create an imbalance of charge? How can you force charge to, break the rules of nature? And personally, there are a couple of ways you can do it. One way is, well, we've already talked about one way, is with friction. If you push electrons around, you can actually physically push them around. And that's what we get when we rub our hair with a balloon. That's what we get when we rub a plastic rod with fur. That's what we get with amber. We're actually pulling the electrons off because they just get a little bit stuck to one of the substances and they get pulled off. And that will create an imbalance of charge, though it is temporary. Another way that we can get an imbalance of charge is because of magnetism. Electrons have a magnetic field attached to them. So if you can actually move electrons around, with magnets. So if you can move an electron around, you get electron movement, you can create a charge imbalance, and that can lead to electricity, or in fact, you can just move the electrons with the magnet, and that will create some kind of field and so on and so forth. So magnetism is another way. The third way that I'll quickly talk about is chemistry. Chemistry is a great way of forcing electrons to move. If I have sodium here and fluorine here, the electron in the sodium wants to jump over to this fluorine because it's almost got a full shell. This will be a more stable energy configuration. So if you can, that is going to be like, it's going to sort of balance the charge out, but it's also going to create an imbalance of charge at the same time. So all those things are sort of related. There are other ways, I think, as well of creating a charge imbalance. One of them is actually, believe it or not, you can actually use heat. You can actually use temperature. I only recently learned about this one too. You can use heat to, if you've got a part of a wire that's hot, a part of a wire that's cool, and the part of the wire that's hot is going to have more movement of electrons. So it's going to be a lower charge, and you can actually get a small, teeny tiny voltage there. But that's it. That's the end of this lesson because I've run out of time here.